Okay, there's its center of gravity, its position, its velocity. Okay, and then here's the lambda of pendulum string 1. Okay, it's not 0, but let's go down. Remember that at a quarter of a second the pendulum was vertical. So if we go down to a quarter of a second, and remember that the lambda for the string, joint 1 of the string, is in AL. No, sorry, AR, R and S, AR and S. Fine, let's remember that. Now let's go down to a quarter of a second. Okay, there's a quarter of a second. Fine. Notice that we're going from, for instance, here's a position of minus 69, minus 7.9, this is now degrees, to 54, no, not degrees, but anyway, you see there we're changing over from minus to plus. We're at the vertical point of the pendulum. So if we now go to the lambda, which is AR and AS, we see that the lambda has right here near the quarter of the swing, in other words when the pendulum is vertical, the lambda has 0x component and a y component, right? So in other words, when the pendulum is hanging straight up and down, there's a lambda that is pointing straight up. Okay, just as a double check of whether lambdas look good, and then following the lambdas we have the kinetic energy, the linear kinetic energy of the pendulum string, the angular kinetic energy of the pendulum string, the linear kinetic energy of the body, of the weight, and angular kinetic energy of the body. And then there's the potential energy of the body, potential energy of the weight, of the string, potential energy of the weight, total kinetic energy, total potential energy. Right. So there's our complete spiel for 1,000 points per second times 10 seconds. So we've got 10,000 points, and I asked for 0.1 of a second just so that we could see second number 10 and just before it and just after it. Okay, and that then concludes that analysis of the three-body system. I'll save that in ODF format. I now go back and load my